Welcome to this course on electrical machine design. In this series, we will explore the principles, materials, techniques, and modern methods used to design electrical machines such as transformers, DC machines, induction motors, and synchronous machines. The course is divided into two modules. Module 1, Fundamentals of Electrical Machine Design. Module 2, Design of Specific Machines and Computer-Aided Design. Let's begin. Module 1, Fundamentals of Electrical Machine Design. Lecture 1, Construction Materials for Electrical Machines. The design of any electrical machine starts with a careful selection of materials. Three categories of materials dominate machine construction: conductors, magnetic cores, and insulating materials. 1. Conductors, cables and windings. The primary purpose of conductors in electrical machines is to carry current efficiently while minimizing losses. Copper and aluminum are the most commonly used conductor materials. Copper is preferred for high efficiency and compact design because of its superior conductivity and mechanical strength. Aluminum, while less conductive, is lighter and cheaper, making it useful where weight and cost are major concerns. Conductors are often drawn into wires or cables, coated with enamel or wrapped in insulation, and arranged in coils or windings. The specification of a cable depends on its current carrying capacity, mechanical flexibility, and thermal endurance. 2. Magnetic core materials. The magnetic core serves to carry and concentrate the magnetic flux in the machine. Silicon steel laminations are widely used due to their high permeability and low hysteresis loss. Laminations are stacked to reduce eddy current losses. For high-frequency machines, materials like ferrites or amorphous alloys are sometimes employed. 3. Insulating materials. Insulation separates conductive parts, prevents short circuits, and withstands mechanical and thermal stress. Materials include varnishes, paper, mica, resins, and synthetic polymers. Insulation classes are standardized based on the maximum temperature they can safely operate at, for example, Class A up to 105 degrees Celsius, Class F up to 155 degrees, and Class H up to 180 degrees. Together, these materials define the electrical, mechanical, and thermal limits of a machine. Lecture 2, Cooling and Thermal Considerations. Electrical machines inevitably generate heat due to copper losses, iron losses, and stray load losses. Proper cooling ensures reliability and long service life. 1. Heating and temperature rise. The temperature rise of a machine is the difference between its operating temperature and the ambient temperature. Manufacturers must ensure that the temperature remains within the limits of the chosen insulation class. Temperature rise data is often represented by heating curves, which show how quickly the machine reaches thermal equilibrium under load. 2. Ventilation and cooling methods. Cooling methods are broadly classified as self-cooled. The machine relies on natural convection and radiation. Force-cooled, fans or blowers push air through ducts in the stator and rotor. Liquid-cooled, water jackets or oil circulation systems are used for high-capacity machines. Cooling curves plot how temperature decreases when the machine is switched off and allowed to cool. Proper ventilation design balances thermal performance with acoustic noise and efficiency. Lecture 3, Winding Arrangements and Flux Distribution. The winding design determines how effectively electrical energy is converted into magnetic flux and vice versa. 1. Winding arrangements. There are several common types of windings. Lap winding, used in DC machines for high current, low voltage applications. Wave winding, suitable for high voltage, low current machines. Concentrated windings, where all turns of a coil are placed in a single slot. Distributed windings, where coil turns are spread over multiple slots, improving the sinusoidal nature of flux distribution. 2. Flux flow in the core. The core guides magnetic flux from the stator to the rotor. Flux distribution depends on slot geometry, winding type, and air gap length. Designers aim for uniform flux to reduce harmonics and improve efficiency. 3. Flux wave approximations. The flux distribution in practical machines is not perfectly sinusoidal. Designers use Fourier series approximations to analyze harmonics. By optimizing slot and winding arrangements, they suppress undesirable harmonics and improve performance. Lecture 4: Principles of Machine Design. Now that we've discussed materials, cooling, and windings, let's turn to the fundamental principles of electrical machine design. 1. Machine output equation. The machine output is a function of electrical loading and magnetic loading. Electrical loading relates to current and number of conductors, while magnetic loading relates to flux per pole. From these parameters, designers derive output equations that link machine size, power, and efficiency. 2. Dimensions and scaling. The main dimensions of a machine, stator diameter, core length, and pole pitch, determine its capacity. Designers scale these dimensions based on the required output rating. 3. General design considerations. Efficiency, achieved by reducing losses in copper, iron, and windings. Thermal limits, ensuring insulation and cooling systems are adequate. Mechanical integrity, the rotor must withstand centrifugal forces, and the frame must absorb vibrations. Economics, balancing material cost with performance. These principles form the foundation for designing specific machines.